Hello everyone! Hypothesis testing has two complementary ways of checking whether a result is significant: the p-value and the confidence interval. Both will be explained and compared. And hello again to this lesson, which essentially has three learning objectives. First, you should know how confidence intervals allow us to assess the compatibility of the null hypothesis with the observed data and make informed decisions regarding its acceptance or rejection. In other words, how confidence intervals can be used to check whether a result is significant and thus represents a deviation from the null hypothesis. You should also understand the p-value and how it differs from confidence intervals when evaluating hypotheses. The term test statistic often causes difficulties in understanding when you hear it for the first time. Test statistics refers to the auxiliary variable required for the respective test. You will also learn what exactly is meant by that. This lesson is divided into 3 chapters. In the first chapter, we use a confidence interval to test whether the data from a sample are significantly against the null hypothesis. In the second, we do the same with the p-value and compare it to the confidence interval. The third chapter briefly explains what is meant by test statistics. Let's start with the significance test based on a confidence interval. The procedure for a hypothesis test is shown on the left. We will go into more detail on each point during this chapter. For this, we use the example of 2 holders glued together. A feature of this connection is the breaking load measured in Newton. If both ends on this assembly are pulled, it will break at the glued point. After a change to the process, an employee now claims that the breaking load is no longer the same as before. The problem is the assumption that after a process change, the breaking load is different from before the process change. So, the characteristic that needs to be examined is the breaking load in Newton. All breaking load tests carried out until the process change resulted in an average breaking load of 100 Newton. Therefore, as a null hypothesis, we assume that the mean breaking load is still 100 Newton. A random sample is later examined for the test. Mu is the mean breaking load of a sample tested after the change to the process, and mu0 is the mean breaking load from the null hypothesis. So, the average breaking load before the process change. The alternative hypothesis is derived from the employee's assertion that the breaking load differs after the process change. It is symbolized in the formula by the sign not equal. The formulation of the hypothesis ultimately also determines how it is tested. This means not only the physical test, but also the statistical evaluation. The best way to choose the correct statistical test is to search for keywords in the hypothesis. Examples are: is different, is higher, or is smaller. In our example, the keyword is different. The bell curve shown here shows the distribution of breaking load values from the past. mu0 is the mean breaking load from the null hypothesis. For the test, we now have to consider that there can be deviations in both directions, up and down. Therefore, we choose a two-tailed test. The acceptance or rejection of the null hypothesis is determined by the position of the test statistic, which has not yet been calculated. In comparison, let's look at another hypothesis. A technician claims that a different adhesive has a higher breaking load in this alternative hypothesis. The key word in this hypothesis is higher. Theoretically, adhesive B could also be worse, but it was decided to look only at one side. This then resulted in the one-tailed test shown here. Finally, let's look at this claim. A customer claims that the breaking load is lower than he knows it from the past. Here the keyword is smaller. So the test is again one-sided, only this time on the side with the smaller breaking load values. So, after this brief introduction, back to our case study. To determine if the hypothesis is true, we calculate the mean breaking load, which is determined through physical testing. Such a variable is generally referred to as a test statistic. In other words, the test statistic is a numerical value computed from sample data used to determine whether to accept or reject a null hypothesis in hypothesis testing. For example, the mean or quantile of a distribution. Two other examples of such a test statistic are the quantiles of, for example, the normal distribution or the t-distribution. These differ depending on the parameter to be examined and whether the variance of the population is known or not. More on this can be found in the corresponding other lessons. Let's look at this frequency distribution of breaking loads from the past before the change was made to the process. An accumulation at the value of 100 Newton can be seen. This is the already known mean breaking load from the null hypothesis. Due to the natural variability of the process, there are also a few breaking loads that are smaller or larger than the mean breaking load. After the process change, a small random sample was taken and the mean breaking load was determined. The mean breaking load of this one sample is 109 Newton, represented by the yellow bar. The following question now arises. How should we know whether this value is not within the expected spread of the process or represents a significant deviation compared to the mean breaking load from the null hypothesis? To answer this question, we first assume that the breaking load values are randomly, normally distributed. Then these values can be described by the normal distribution curve as shown here. The area under the curve represents 100% of all possible values. Our investigation aims to identify whether there is a significant deviation. To be able to make this decision, we need limit values. If these are exceeded, there is a significance. Derived from the assertion from the alternative hypothesis that the breaking load is different after the process change, we decided on a two-sided test. So we define a lower and an upper limit. Of course, we don't do this randomly. Instead, based on the historical data, we chose the limits such that there is a 95% probability that the population mean is within these limits. The area between the lower and upper confidence limits is called the confidence range or interval. Again, based on historical data, there is a 95% chance that the population mean is within this range. Now that we have determined the limits for our chosen confidence interval, let's return to our question from the beginning. This was, how should we know that the mean breaking load of 109 Newton, determined after the process change, is not within the normal spread of the process that was to be expected anyway, or whether it represents a significant deviation. As you can see, the value 109 is well outside the confidence interval. So this result is significant. Therefore, the null hypothesis is to be rejected. But before we formulate the conclusion, let's discuss the following. The significance level is abbreviated as alpha. This significance level is also referred to as the error probability. Why this? We said at the beginning that the null hypothesis is assumed to be correct. This means there is a probability of alpha, for example 5%, that a correct null hypothesis will be incorrectly rejected. Hence the term error probability for alpha. Incidentally, if a correct null hypothesis is wrongly rejected, this is called a type 1 error. On the other hand, if the null hypothesis is wrongly accepted, this is a type 2 error. At this point, the physical breaking load tests would actually be carried out. Based on these test results, you then calculate the value that we previously called the test statistic. For example, the mean breaking load. But we had already set that to 109 Newton. Finally, the result is formulated in the original problem's context. Because the sample mean is outside the confidence interval, we reject the null hypothesis H0 and conclude that the mean breaking load is different after the process change. This chapter briefly explains what the p-value is and how it differs from confidence intervals when assessing significance. To compare the p-value with the confidence interval, we continue the example from the previous chapter. However, we will only use the excerpt shown here. That keeps things a little clearer. Again, to repeat. The significance level, or the error probability, alpha, is our standard of proof. For example, an alpha of 0.05 means a 5% risk of deciding that an effect exists when it doesn't. So, to reject a correct null hypothesis. In our example, one of the limits on the right is at the mean breaking load of 109 Newton. The p-value now indicates how likely the sample result is, or more extreme results are, assuming the null hypothesis is true. The p-value is, so to speak, the observed level of significance. In our example, the p-value is the probability of getting 109 Newton or higher values. Such a p-value could have a value of 0.01, for example. So, if the p-value is less than the alpha significance level, we reject the null hypothesis. That is, the p-value is on the right side of the limit. If the p-value is greater than or equal to alpha, we do not reject the null hypothesis. That is, the p-value is to the left of or at the limit. At this point, I would like to emphasize a few points separately. What the p-value says and what it doesn't. What is the p-value? The p-value indicates how likely the sample results are, or more extreme values, assuming the null hypothesis is correct. P-values can indicate how incompatible the data are with a specified statistical model. What the p-value is not. The p-value is not the probability that the null hypothesis is correct. The p-value is not the probability of rejecting a correct null hypothesis, so of making a type 1 error. The p-value does not measure the size of an effect or the importance of a result. Relevance. Even if the p-value indicates statistical significance, this does not necessarily mean it is also of practical relevance or benefit. It is important to interpret the p-value with other statistical values and background knowledge of the subject area to draw meaningful conclusions. I could say a lot more about the p-value, but these are the most relevant points for me at this point. Finally, I would like to comment on the test statistics briefly. So, the values or sizes are determined by physical tests and are the basis of a decision. We chose the mean breaking load as the test statistic in our example. Consequently, the units on the x-axis are newtons, and the mean is the mean breaking load calculated from the data. More often, however, standardized distributions such as the standard normal distribution are used because this is simply more convenient. In the case of the standardized normal distribution, the quantiles of the normal distribution are on the x-axis instead of the breaking loads. And instead of the mean breaking load, the center has the value 0. The z value for the x-axis is calculated using the formula shown here. Values for the limits are then taken from the tables for the standardized normal distribution, for example, but can also be calculated with Excel. The same applies if the underlying distribution were a t-distribution. The t-distribution is used when the population variance is unknown. In practice, one usually does not know the variance of the population. Then the test statistic would not be z0, but t0. More on this is explained using examples, including calculations in other lessons. So, that's a lot of information. Therefore, I will summarize the 4 most important key messages again. A confidence interval is calculated from a sample to obtain a range for where the population parameter, the mean, is likely to reside. If the test statistic is outside the confidence interval, then the result is significant. The p-value now indicates how likely the sample results, or more extreme results, are, assuming the null hypothesis is correct. The p-value is the observed significance level. When the p-value is less than the significance level alpha, we reject the null hypothesis, meaning the result is significant. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye!